Okay, so I wanted to make a video on cephalosporins. I've been studying them lately and trying to understand truly why they had to change and why they continue to evolve and why the coverage of bacteria is changing as a result of the changing structures of them. And at first, my approach was to try to memorize the differences, off of a chart. But I think it's better to really look at the molecular structure and understand why chemists have been changing the structure and exactly how that's been targeting different bacteria. So before we get into that, I think we should just overview quickly, just a quick review of the difference between gram-positive and gram-negative bacteria. Right, the gram-positive have this large peptidoglycan outer layer, right, sitting right above their cytoplasmic membrane, right. Our cells have cytoplasmic membrane, pretty much all living things have cytoplasmic membranes, but bacteria are special that they have the peptidoglycan, right, protein, sugar, large wall out there. So those are the gram-positive. Now, the gram-negative also have a peptidoglycan layer, which is what some of the early antibiotics target and try to destroy. But you can see that the gram-negative, on the outside, they have a cytoplasmic layer, an additional one. So it can actually be difficult for something that's trying to target this peptidoglycan layer to get through that, whereas it's a little bit easier on the gram-positive. Just a kind of an easy way of remembering this difference is gram-negative. You see there's a thin line with the negative. I like to think of the small, thinner layer of peptidoglycan for gram-negative. That's kind of a quick way to think about it. So penicillins, some of the earliest antibiotics, penicillins, they were targeting what's known as the penicillin binding protein. And pretty much what this is responsible for is forming those peptidoglycan layers. It forms these cross links up here. So if you can find something that inhibits that enzyme, goes in there and straight up just blocks it, you can prevent further synthesis of here. I kind of drew these brown lines here to represent the cross links, and cephalosporin gets in there, blocks this penicillin protein, and eventually nothing can be formed. And as a result, the bacteria either lyses out of a result of hydrostatic pressure, or if it's trying to divide and go through binary fission, it really can't do so if it's not allowed to make even more peptidoglycan layers, right? You can't really divide if you can't make a larger organism. So the penicillins went in there, bound that enzyme within this layer and prevented it from forming even more cross-links and larger peptidoglycan layers. So now we can kind of get onto cephalosporins. They bind the exact same enzyme, but they have a little bit of a different structure now. You'll see here, you probably don't know what it is. I didn't know what it was, but this is called a beta-lactam ring, right? You got that hexagon here and then just this square there. That's kind of the center of the molecule. Those pretty much remain unchanged throughout the evolution of cephalosporins. That's why it's a beta-lactam. But on these outsides here, I'll refer to these as functional groups. These are actually exchangeable, and chemists have found ways of synthesizing and changing the outsides of those so that they target the enzyme a little bit differently, right? So the first generation cephalosporins were effective at binding those enzymes in the peptidoglycan layer. So they were good at covering gram-positive bacteria, right? Because that's on the outside. It was easy to do that. But it was difficult to get to that peptidoglycan on the inside of the gram-negative. And as a result of using cephalosporins, the bacteria eventually became resistant, and chemists realized that they had to make some changes, right? And there's also some natural esterases in the body. The esterases act on the cephalosporin molecule, and they realized that it was quickly metabolizing it, right? So it made it even more difficult for those molecules to get inside, possibly to fuse through that top layer of the gram-negative, if they were being metabolized so quickly. So they wanted to make sure that they changed the molecule so it didn't fit into these esterases as well. So you can notice these functional groups are a little bit different. This one is a little more bulky, right? It has this nitrogen on the outside here, and this has been swapped as well. My hypothesis, I don't know if this is true, but this makes sense to me and helps me remember it, is that because these were not being metabolized as quickly, they last longer and the concentration is going to be higher systemically, and that as a result, it's going to be able to diffuse through that cytoplasmic membrane somehow and target that peptidoglycan layer and cause the bacteria to lyse. Now, of course, bacteria evolved and realized that they could create what we know as beta-lactamases, right? These resistant enzymes that go out and actually cleave the beta-lactam ring here. So we noticed a lot in the second generation, although it was expanding coverage to the gram-negative. These beta-lactamases were really a problem in that they were starting to cut the cephalosporins and breaking apart that beta-lactam ring. So we thought, hey, what can we do about this? How can we prevent this from happening? And of course, the right answer is introducing this really large molecule on the side of the cephalosporin, creating what you probably remember in organic chemistry is steric hindrance, right? You make a much larger molecule, it's less likely to fit into that active site. And they also added this carboxylate down here, which is a charged molecule. There's this charged nitrogen right here. And if you remember, charged molecules actually can pass through transmembrane proteins, right? So in these gram-negative bacteria, they actually have these porin molecules. And I like to imagine transmembrane proteins as just having a bunch of alternating positive minus amino acids on the inside that help to diffuse molecules through them. So now that this cephalosporin, this third generation, has this charged features to it, it was actually able to diffuse much easier through, maybe I can pull this up here, it was easier for it to diffuse through these porins and have access to the peptidoglycan layer on the inside, right? So quick review, the first generation easily could target this outside, the penicillin binding protein, and inhibit it, but we had these natural esterases in the body that prevented it, or that metabolized it too quickly, and then the bacteria also became resistant in the sense that they were making their own beta-lactamases that were breaking the molecule down. So we had to make the molecule larger, and as a result of making it larger and adding charges, it was now able to diffuse easier through the cytoplasmic membrane, right? And as a result, this charged molecule, we're expanding the coverage now to more to gram-negative. It's actually going to be much more preferential for gram-negative at this point. And so at this point, they realized that this is a pretty good starting point, having some charged qualities, adding some steric hindrance to it, and they just kind of start making some small, minute changes and increasing the solubility of it. Fourth generation is most notable for having better GI solubility and can even cross the blood-brain barrier for infections that you're dealing with there. And just note that this beta-lactam ring is unchanged throughout. You're really just swapping the outsides here, kind of like Legos, which is pretty sweet. And as a result, we're able to target different bacteria with different structural features just by swapping out functional groups. So I think this is probably something you want to see here is just when we start at the beginning, right, it had good gram-positive coverage. As a result, it's kind of gotten broader coverage towards the gram-negative aspect now. And I actually don't know much about the fifth generation cephalosporins. Maybe that's a project for you to go figure out why this molecule itself is better and has better coverage. So